In this video, I'm going to introduce the unit circle and how it can be used to evaluate certain trigonometric functions, especially sine, cosine, and tangent very easily, but similarly cosecant, secant, and cotangent can be computed as well. The unit circle can also be used to convert angle measures from degrees back and forth between radians. So the first thing that we're going to do with this unit circle is to place the degree angle measure of each angle on the dashed lines. We're going to place the radian angle measure on the solid lines, and then I'll show you how to create the coordinates of each indicated point on the outside of the circle. So let's start with the degree measurement, since that's what we're most comfortable with, I'm sure. It's customary on a coordinate system to always start our angle measurements at the positive x-axis. So you can imagine that there's an x-y axis on this circle, and the circle has a radius of 1. So each of these positions are 1 unit above and below the origin. Now, when it comes to indicating angle measures, we always start here at the positive x-axis, and this angle measure, with both sides of the angle lying in line with one another, contains an angle measure of 0 degrees. Now, to make this a little bit more clear, what I'm referencing is the angle measure formed by the positive x-axis and the angle measure indicated on the circle. So now that we've got some actual distance between the two side lengths, let's consider this angle measure here. The first line in this particular unit circle has an angle measure of 30 degrees. If I had taken a protractor and measured from this side along the positive x-axis to this side here, this is a 30-degree angle measure. The next angle measure is a total of 45 degrees, and it's a 15-degree difference between the second angle and the third. So this changed by 15. Now you may recognize that spacing is the same between this angle measure and the next, so we'll state that this angle measure is 60 degrees. Now the next space is a little bit larger. In fact, it's the same size as this space was before, so there's a 30-degree difference, and we would call this a 90-degree angle. And hopefully that's fairly obvious to you. If I had measured from the positive x-axis to the positive y-axis, this angle measure appears to be 90 degrees, or a right angle, and that's entirely true. Now we're going to continue to mark these angles around the unit circle, and beyond this angle to the next one is a difference of 30 degrees, so this is going to be 120 degrees. Then we see a change of 15 degrees, and that's going to be marked as 135. Then 150, because again another difference of 15 degrees. And then finally a difference of 30 degrees, or 180 degrees. And hopefully there isn't any confusion here. If I had measured from the positive x-axis to one of these angles over here in the second quadrant, we would note that this is an obtuse angle, and it has to be greater than 90 degrees, but less than 180. And that's exactly what these measurements are indicating here. Now, if we reflex beyond 180 degrees and end up down here, certainly we could measure the angle from this position to this one, but that's not common. That's not typical in the unit circle. When we're talking about rotations of side lengths to produce a new position, we generally rotate counterclockwise. And in this case, we've bent beyond 180 degrees, 30 degrees beyond 180 to be precise, and we've reflexed this straight edge, this straight angle beyond 180 degrees, and this is going to be measured 210 degrees. When dealing with physical objects, we tend not to see angle measures in degrees beyond 180, but if you are thinking about an object that rotates or spins, you might be familiar with this notion of measurements being greater than 180 degrees. So we'll keep going. The pattern continues from before. This next angle increases by 15, so we'll call this 225 degrees, then 240, and then finally 270 degrees. For the final quadrant, an additional 30 degrees at this position is 300 degrees. An additional 15 to this position is 315 degrees, then 330, and then we end up with 360, back where we started. If we had an angle measure that contains sides that start at the positive x position on the x-axis and ends at the same position, we can consider that a 0-degree angle, or if necessary, we can consider that a 360-degree angle if it opens all the way around. Now that stands to reason that if we were to rotate more than one time around a circle and end at a new position, that would create a new angle measure. Now if I had a rotation that was one complete rotation plus another 30 degrees, we might consider that 360 plus 30, or 390 degrees. And that would be okay. We're not going to mark that on our unit circle, but this would be okay to note, and this position, while it's the same as 30 degrees, would be considered a coterminal angle. So coterminal to 30 degrees. Two angles whose terminal side, or second position, land in the same position would be considered coterminal. But again, that's not important for us to report on this unit circle, and it won't be quite so helpful in immediate activities in this particular unit, so I'm going to take those off. Now, as a reminder, a unit circle is simply a circle with a radius of 1. And this radius of 1, or the circle I should say, is centered at the origin of an xy coordinate system. So if I were to consider a circle whose radius is equal to 1, and then ask about the circumference, well, hopefully you recall from geometry days that circumference is equal to 2 times pi times the radius, which in this case, the circumference of the unit circle is simply 2 times pi times 1, or 2 pi units. If the length around the circle is 2 pi units, and I subdivide that length into the same positions indicated by our degree markings, the important degree markings from our unit circle, then it would be nice to know how long each of these positions are. What's the length around the circle from starting point to this position? Or what's the length around the circle from starting point to this position? And so on. Well, that measurement in length is what we call the angle measure of a radian. A unit circle has a circumference of 2 pi radians. So if we were to mark our radian angle measures on the same unit circle, we might see the following. Number 1, this position is the same as 0 degrees, so therefore it has 0 radians. If I were to measure the length of this unit circle to this position, we could perform the math. It's 30 degrees out of 360 times 2 pi radians, because 30 degrees out of 360 represents the proportion represented by this arc, and 2 pi would represent the entire circle. So the portion of the circle associated with this position would simplify to pi over 6 radians. The next position, when rotating from the positive x-axis to this position, could be calculated the same way. We would use 45 divided by 360 times 2 pi radians, and that would reduce to pi over 4 radians. Now perhaps you've noticed that when indicating degrees we always use the degree symbol, and when indicating radians it's common practice to write RAD afterwards. It's also common to note radians without any symbols whatsoever. this next position would reduce to pi over 3 radians, and it's perfectly fine just to report that as pi over 3. No additional symbols or phrasing is necessary. So I'll continue that process all the way around. This next position, after the conversion is complete, will indicate that this angle measure is pi over 2 radians. The next one would be positioned at 2 pi divided by 3 radians, 3 pi divided by 4 radians, and then 5 pi divided by 6 radians. There are lots of ways to determine the radian angle measures inside of a unit circle, and one technique was to use the process that I just identified a minute ago. The expectations for my students in this class are to memorize the unit circle, and it's up to you to determine the best memorization method that works for you. If you just want to memorize the positions, that's fine, or if you want to learn a technique that would help you repeat the information on the unit circle, then that's fine too. I would encourage you to look that up on your own or see me for extra help and practice. So this position here, if I had measured around the circumference of the circle to this point, you'll notice that's half of the circumference, or half of 2 pi, and that's why we landed on pi in this position. This angle measure in radians would be recorded as 7 pi divided by 6, 7 pi over 6. Then we have 5 pi over 4 and 4 pi over 3. And then lastly, 3 pi over 2 in this vertical position. For the last quadrant, we move on to 5 pi over 3, 7 pi over 4, 11 pi over 6, and then we can call this last one a full rotation, 12 pi over 6, or reduces to 2 pi radians. Now, for the last component of the unit circle that we have to have memorized, we're going to consider the coordinates of the unit circle, the coordinates of these positions in the unit circle. And a few of them are pretty easy to identify. For example, this coordinate here, if I know that this circle is centered at the origin and has a radius of 1, well, it should be easy to tell that this position is 1, 0. And this position over here is negative 1, 0. And here we have 0, 1. And here we have 0, negative 1. Those are easy to identify in the unit circle. Finding the remaining coordinates, those are a little bit more challenging, and I'm going to use a blank copy just to illustrate the point that I'm about to share next. We're going to focus on this coordinate first, and what I'd like for you to consider is a right triangle that sits inside the first quadrant, and the white triangle, this right triangle, is generated by the angle measure associated here and this coordinate here. So whatever x and y come out to be, as it turns out, is going to be the length. X is the horizontal length of the triangle, and y is going to be the vertical height of the triangle. And so while we're talking about right triangles, we might also recognize this as the opposite side length to this angle measure. And the x-coordinate is the adjacent side to the angle measure. What's particularly helpful about this being a right triangle is that the distance from the center to this point is the radius of the circle, and the radius of the circle is always 1, because this is a unit circle. So if I wanted to calculate this x value first, if I wanted to calculate the x-coordinate, that's not too hard to do. I have to find the adjacent side length, and I know what the hypotenuse side length is in this right triangle. I also know that this position here specifically is located at the 30-degree angle measure. So if I set up my calculator to solve, sine of 30 degrees must be equal to the, sorry, not sine, we want the x value first, so we'll use cosine, because this is an adjacent side divided by the hypotenuse. We'll set cosine of 30 degrees equal to x divided by 1. Well, as it turns out, x divided by 1 is simply x, so the result of cosine of 30 is equal to precisely x. Now, according to the calculator, cosine of 30 degrees is equal to 0.8660254, blah, 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 blah. There's lots of decimals here. It's a non-terminating decimal. It's an irrational result. And that would be a difficult number to report for the x position or x value of this particular coordinate. So instead, what we tend to do is we tend to write this as a radical or a fraction of radicals. And it turns out that the value 0.8660, etc., is exactly the same as the square root of 3 divided by 2. And while that's still not perfect, it's a whole lot better than writing an infinite amount of decimals. Now for the y value, in a similar argument, we can say that sine of 30 degrees must be equal to y divided by 1. And y divided by 1, of course, is just y, so sine of 30 degrees must be the value for y. And this is pretty nice because the calculator returns a result of 1/2. Evidently, the y coordinate in this position is 1/2, or 0.5. And if you recall the special right triangle rules from your geometry class, you should recognize that the side length across from a 30-degree angle measure is always half the length of the hypotenuse of that right triangle. Now, speaking of geometry, there are nice geometric explanations as to why the fraction radical 3 over 2 and the fraction 1/2 are appropriate for these positions. We're not going to cover that in this portion of the class, but if you'd like to see that as an explanation or example, I'd be happy to show you. Let's go ahead and complete the remaining coordinates, and we could calculate the rest of them using the same methods as before, but I'll just share these with you in the interest of time. So as we said a moment ago, the x value at the 30-degree or pi over 6 radian angle measure is radical 3 over 2, and the y value at this position is 1/2. In the next position, the x and y values are the same because we're now dealing with a 45-degree right triangle, and a 45-degree right triangle is isosceles. Now its x value is radical 2 over 2, and the y value is also radical 2 over 2. In the next position, the 60-degree or pi over 3 radian angle measure, the x value ends up being 1/2 of a unit, while the y value is radical 3 divided by 2. And hopefully you can see that connection. If I were to look down at the x-axis, you'll notice that the position correlated to this data point is halfway between the origin and this position. So our x value is 1/2, and the y value, well, the y value here is closer to 1 than it is to 0, and again, we calculated this number before to be 0.866 something. So to say that the y value is pretty close to 1 is a pretty good result. I think it's a believable value. As we continue around the circle, we'll start to see patterns develop. This position over here is the same height as this position here, so that tells me they share the same y values, radical 3 over 2, and as it turns out, the distance between the origin and this position on the x-axis is negative 1/2. It's just leftward 1/2 of a unit instead of being rightward 1/2 of the unit, like this position. In the next coordinate, we'll report that as negative radical 2 over 2, positive radical 2 over 2, negative radical 3 over 2, positive 1/2. And we'll continue that pattern as we rotate around the circle. Take note of where the signs change. Here are the results for the next 3 positions. And for the final 3. Now at this point, it's worth noting, down here in this example, it was the sine function that was used to compute our y coordinates. So in general, we often say this, that sine of some angle measure is equal to the y coordinate inside the unit circle. As it turns out, when we look at our results here, all of the y values were negative in these positions here. And actually, I'm looking at the questions here. They're actually asking for positive values. So let me say this a different way. All of the y coordinates are positive in these positions here. All y coordinates are positive. So that tells me that sine of theta, sine of some angle measure, will always be a positive value, will be I'm just going to say positive y value in quadrant 1 and quadrant 2. These coordinates in this group are labeled as quadrant 1 and quadrant 2. Hopefully you recall this from your geometry days. 3 and then quadrant 4. So anytime that I ask for sine of an angle measure in the first or the second quadrant, my sine result will always come out to be positive. So which trig function is positive in the first quadrant? Well, sine is positive in the first quadrant. Which trig function is positive in the second quadrant? Well, sine is positive in the second quadrant, but it is not positive in the third or the fourth. Now, similarly, we noted that cosine was the method used to solve for our x component. And cosine of some angle measure will always be that x component. And as it turns out, our x components are positive in the first quadrant, not the second or the third, but also the fourth quadrant. So, which trig functions are positive in the first quadrant? Well, we now see that cosine is positive in the first, but not the second. Cosine is positive in the third, but not the, cosine is positive in the fourth, but not the third. Now, lastly, a word about tangent. This one takes a little bit of thought, but hopefully you recall that tangent was described as the trig ratio, opposite divided by adjacent. So if we're talking about the opposite side length being divided by the adjacent side length in terms of x and y, then what we can state here is that the tangent result of some angle measure will simply be the y coordinate divided by the x coordinate. We may not have to reach for a calculator after all to calculate this tangent measurement. So where will y divided by x be positive? Well, the only time that I can have two numbers divide one another and generate a positive result is if both elements are positive, so x and y have to be positive, or if both coordinate values are negative. A negative number, y, divided by another negative number, x, will produce a positive result. So again, which trig functions are positive in the first quadrant? Well, we now know that tangent is going to be positive in the first quadrant, but not the second or the fourth because the signs of the components are different. Tangent is positive in the third quadrant. So by taking note of these results, we can use them while problem solving applications in the future. Perhaps we need the location of a robotic armature to be in a certain position. And if we're using trigonometry to locate that position relative to a starting point, then we would certainly want to know what the trigonometric computations end up becoming, whether they're positive, negative, and what their numerical values are. We'll discuss more about that in a future video. For right now, what I would recommend that you do is print off a couple additional copies, if you didn't collect enough from class, of this unit circle, a blank copy of it, and start practicing memorizing this. I would expect you to be able to recite all angle measures in degrees and radians, as well as all coordinates and the answers to the questions at the bottom in under 5 minutes. You would be timed, or I could put together a timed quiz if I feel so inclined, and I would expect you to be able to recite and recreate this entire unit circle in under 5 minutes. The record in my class is much less than that, and I know this seems like a lot to do in 5 minutes, but certainly it can be done. So start memorizing these components now, and come see me if you have any questions, and we can chat about it in class or during office hours. Thanks for watching.